Let's consider solving some of the problems in this section. Here we want to compute the limit. For this first problem, we simply compute it directly. This is the limit as x approaches 2. We're here. This just becomes 2 to the third power, and that just gives us 8. Likewise, in this manner, with number 5 and number 12, also for numbers 14 and 20, the limit of the function is continuous as x approaches the value of a or 2 or 1. The function is continuous. If the function is continuous, then you can evaluate the limit at the designated values. So this becomes the limit as x approaches 1. This is 2 times 1 to the third minus 6 times 1 plus 5. And the limit here of a constant is a constant. Likewise, the limit of a constant is a constant. So we get 2 minus 6. That gives us negative 4 plus 5. We just get positive 1. Put a note here. A function is said to be continuous at x equal to a if the limit exists at f of a. So a function is said to be continuous at x equal to a if the limit exists at f of a. So I believe we have that same thing here for number 14 as well. And so we have the limit as x approaches 2. This is the cube root of 12 times 2 plus 3. I just evaluate the limit function at the value x here equal to 2. X approaches 2, but we notice that when x is equal to 2, we get something that is defined. So we have the limit as x approaches 2. We get the cube root of 27, and that's just 3. Likewise, for this one, if you evaluate the limit at x equal to 1, we get something that is defined. It's the limit as x approaches 1. Here, evaluate this function at 1. We get 3 plus 5 gives us 8 all over 2. So that just gives us 4. The same thing here. The limit as x approaches 3, we get the square root of 3 plus 6 all over 3 plus 2. So we get the square root of 6 plus 3, which is the square root of 9. So we get 3 there, just divided by 5. Number 27, the limit as x approaches pi over 2 of sine of pi over 2. Well, the limit of a constant is a constant. Sine of pi over 2 is just 1, so the limit of 1 is just 1. We evaluate this one. So the limit as x approaches pi. This tangent can be looked at as sine over cosine. So this is sine x all over cosine x. We get the limit as x approaches pi of sine pi divided by cosine pi. Well, sine pi is 0 and cosine pi. That just gives us -1. So here we have the limit as x approaches pi of 0 over -1, and we just get 0. We would have to deal with asymptotic values and examine the limit if this was cotangent. That is, if it was the limit of cosine over sine. Once we get that 0 downstairs, then that gives us a bit of caution, and we have to employ other methods. Number 29, the limit as x approaches 1. We're going to go ahead and just plug in x equal to 1. So this gives us cosine of pi over 3. And cosine of pi over 3 is a constant. Limit of a constant is a constant. So this just gives us cosine of pi over 3. Now, if you're like me, you don't keep a calculator on you and you kind of get rusty with your unit circle. So I just employ what my instructor gave me years ago. Let's take an equilateral triangle with all sides the same. Let's say 2. Let's bisect 1, so this is 1 and 1. These are all 60 degrees. And then if we bisect this guy, then you know that becomes 30 degrees there. Well, 30 degrees or pi over 6 and 60 degrees or pi over 3. You find this height there using the Pythagorean theorem, you get the square root of 3. And so talk about the cosine of pi over 3 is cosine of this 60 degrees. So that's going to be 1 over the square root of 3. So is everybody fine with that? So if that be the case, we move on and let's look at the next few problems. Let's see. Well, let's look at this particular problem. here, when I plug in x equal to 4 into this, I get 4 minus 4 is 0. Then I get 16 minus 16 is 0. We have an indeterminate form. If it's indeterminate form, we can do one of three things. Calculus 1, we do one of two things. We can either, so we say that indeterminate form implies that we can solve the limit by factoring if we can, or rationalization, or number 3, we save this for a later time, L'Hopital's rule. Okay. Well, I can factor this denominator, so we just employ the first one, which is factor. It's the limit as x approaches 4. You get x minus 4 in the numerator. You factor downstairs x minus 4 times x plus 4. We can cancel. So x minus 4's cancel out. You have left the limit as x approaches 4 of 1 over x plus 4. That just gives us 1 over 8. Let's look at another one. Here, if we plug in x equal to 4 of this limit, then we get the square root of 9, which is 3 minus 3, gives us 0. And then all over 4 minus 4 is 0. Again, another indeterminate form. So if that be the case, we said that 1 we can factor. Well, we can't factor this. Number 2, we can rationalize if you have a radical. Well, we'll employ that, or you can use L'Hopital's rule, and I haven't discussed that yet. So we're going to rationalize. You remember rationalization, it depends on what you want to rationalize. Basically, rationalization means you want to get rid of the radical. Here we're going to get rid of the radical in the numerator. So we're going to multiply to the numerator and denominator by the conjugate of the numerator. So this is the limit as x approaches 4. This is the square root of x plus 5 minus 3 all over x minus 4, and this is times the square root of x plus 5 plus 3. It's the conjugate, and then divided by the square root of x plus 5 plus 3. So what we have, if you think about it, is this times this guy, right? And then this right here times downstairs over there. So when you do that, we end up with the limit as x approaches 4. First time the first is x plus 5. The outer times the outer and the inner times the inner will cancel out. All you have left then is the last time the last. That's minus 9. This is all over the x minus the 4 times parentheses the square root of x plus 5 plus 3. Now this is, when we simplify that, this is the limit as x approaches 4. That numerator is just x minus 4. It's all over x minus 4 times parentheses there, the square root of x plus 5 plus 3. You can see what cancels out. The x minus 4 up in the numerator and denominator cancels out. So we have left the limit as x approaches 4. This is 1 up top divided by the square root of x plus 5 plus 3. Now if we plug in x equal to 4 for x, we do not get something undefined, and we do not get anything that's indeterminate. We end up with 1 all over, this is the square root of 9, which is 3 plus 3, so we get 1 over 6. We have two special trigonometric limits. That is, the limit of sine x divided by x is equal to 1. That is, as x approaches 0. And then number 2, the limit of 1 minus cosine x over x as x approaches 0. This is equal to 0. Now, the proof that is standard for 1 and 2 is somewhat, it's a little lengthy. My proof cheats and assumes that we can use L'Hopital's rule. Using L'Hopital's rule, the proof of that is just the derivative of the numerator divided by the derivative of your denominator, and then you get what you want. Well, let's see. We'll take these two theories and just use them to our advantage to find these limits. So I have to be able to work the limits of these following problems here, I have to be able to see these theoretical conclusions within the problem. So if you take this first one, I see it, but there's a 5 downstairs. I can pull that 5 out. It's a 1 over 5 times the limit as x goes to 0 of sine x over x. You see that? Let me write it a little bit larger. So this is 1 over 5 here now times the limit as x goes to 0 of sine x divided by x. Now the limit of sine x over x as x goes to 0 is just 1. So we get 1/5 times 1. So we end up with just 1 over 5. Now this one we can break it up into two parts. If you think about this, this is the limit as x approaches 0. This is 3 minus 3 cosine x all over x. You can break this up into two parts. And, excuse me, I can't say I'm on medicine. I need some medicine. We're going to use this guy right here. And so let's put that 3 back where it was. And I get kind of shook up a little bit sometimes. You know, like Elvis. I'm all shook up. So anyway, I'm going to write this as the 3. We're going to factor that out times what I have left, the limit as x goes to 0 of 1 minus cosine x over x. So the limit of 1 minus cosine x over x is x approaches 0. That's equal to 0. So here we get 3 times that 0, and that's 0. So we move here. Now notice how this can be written. This is the limit as x approaches 0. I'm going to take that sine x that's there, divided by one of the x's downstairs, times, the limit can be looked upon as the product of two limits. Or you can look at the limit as being the ratio as well. So here, this is the limit of 1 minus x 1 minus cosine x, and this is all over x. So the limit as x goes to 0. Okay, that's better. Well, we have the limit of sine x divided by x. That tells us that guy is equal to 1. And the limit of 1 minus cosine x divided by x goes to 0. That's equal to 0. So we get here 1 times 0. And that just gives us 0. Well, let's look at this one. This is the limit of sine x times the limit of sine x divided by x. So this is the limit as x goes to 0 of one of those sine x's times what we have left, the limit as x goes to 0 of sine x all over x. Well, the limit of sine x as x goes to 0 is just 0 times the limit of sine x over x goes to 0 is 1. So we end up with 0. If we take this one, now this is kind of tricky. This wants to use this theorem here. So you got to be, excuse me. Boy, I tell you. It wants to use this guy right there. But it looks like it a little bit, but not all the way. So we have to work on it. So here's what we have. If this is going to be sine of x in the numerator, then I have to have that x downstairs. Well, here x is 3t. So we can manipulate that. One, we can pull out the 1/2. So this is times the limit as t goes to 0 of sine 3t all over t. Well, I can't say that this is equal to 1 yet because I need a 3t downstairs. It's just a 3t in that sine 3t is only just a t here, was a 2 multiplied to that. So I'm going to multiply by a sophisticated 1, and here this 1 would be 3 divided by 3. So when I do that, I have in the front this 3 up top divided by that 2 times the limit as t goes to 0 of sine 3t all over 3t. All right. But this gives us 3 over 2 times 1. That's according to the theory that we have up above. So that's just equal to 3 over 2. So what about this particular problem? In in the lecture earlier, we proved the limit using delta epsilon. So we want to make use of that. We just mimic the proof to be able to show that that this is the case. Now the limit here would be if I plug in x equal to 8. So here I get 32 plus 8. That gives me 40. So we say that this limit is true. So the limit of 4x plus 8 as x approaches 8 is equal to 40. We say if and only if, this is by definition, for every epsilon positive. Epsilon gives the boundary restriction for the y values or the function values. Does there exist a positive delta such that whenever zero less than or equal to the absolute value of x minus here c is the 8, less than some delta, this implies that the absolute value of the function f of x minus this limit that we're proposing to be the limit is less than some epsilon. We must find a suitable delta. A suitable delta that is related to the epsilon. So what we have here is that if 0 is less than the absolute value of x minus 8 is less than delta, we assume that, then to show that the absolute value of the function, which was 4x plus 8 minus the limit, which was 40. Simplify that. This is equal to the absolute value of 4x minus 32. Now, this is less than or equal to, factor out the 4. This is 4 times the absolute value of x minus 8. This is strictly less than 4 times delta, because the absolute value of x minus 8 is less than delta, so it's just 4 times that delta. Well, we can set this equal to epsilon, and we get it. So this implies that delta is equal to epsilon divided by 4. So for part A, here, this number is epsilon. This is epsilon. And then for the second one, this is epsilon. So it said, if you know the epsilon, can you find the delta? It said find the largest value for delta. So for part A, if epsilon is equal to 0.01, then delta is equal to 0.01 divided by 4, which is 0.0025. Then for part B, if epsilon is equal to 0.001, 5, then delta is equal to 0.005 all over 4. This gives us 0.0025, and this is 0.00125. Okay. And let me check that on my calculator. 0.01 divided by 4 is 0.0025. Excuse me. And down here, that's the 0.00125. Okay. Now, just one more. Here it says find the limit. I'm going to work this out, and then when I get through working out, I'm going to show you what it is. All you want to do is just simplify that. But you recognize what's going on. A couple of things is going on. Well, first, let's go ahead and just solve it. And then when we get through, we'll talk about it. So this is the limit as delta x goes to 0. I'm going to simplify what they tell me. This is x plus delta x to be squared. So this is x squared plus 2x delta x plus delta x squared minus 7x minus 7 delta x plus 7, run the negative through the parentheses, minus x squared plus 7x minus 7. This is all over delta x. Now some things to cancel. What's going to cancel is everything that doesn't have a delta x in it for right now. So x squared minus x squared cancels. Minus 7x plus 7x cancels, and x minus x cancels. So we have here what's left is the limit as delta x goes to 0. I have 2x delta x plus delta x squared minus 7 delta x. 2x delta x plus delta x squared minus 7 delta x all over delta x. You can factor delta x from the numerator. It doesn't factor out, but you can factor it over. How come it doesn't come out? The limit is with respect to delta x, so I can't just get rid of it. So I can put it here, delta x times parentheses, 2x plus delta x minus 7. This is all over delta x. Now delta x divided by delta x cancels out. I have left the limit as delta x goes to 0, and this is 2x plus delta x minus 7. Now as delta x goes to 0, that delta x goes to 0. So you have left the limit as delta x goes to 0 of 2x minus 7. Well, the limit of 2x minus 7 as delta x goes to 0 is a constant because there's no delta x's here in the function value anymore. So the limit of a constant is a constant. This is just 2x minus 7. Now what is this? This is the derivative. derivative so that's the derivative. That A got mixed up in there. Dang on it. That dang on it. Crazy A. It's the derivative of what? It's the derivative of the function. What's the function? There it is right there. This is the definition of the derivative. So the function is f of x is equal to x squared minus 7x plus 7. Take the derivative f prime of x, and that gives you 2x minus 7. That's all you found, right? Well, whether or not we call it the derivative or not, that's what it is. Now, where does that come from? It comes from the definition of the derivative. And that definition says that f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. This is the derivative. Thank you.